Basic Econometrics.
In this chapter, we want to learn more about the behavior of the estimator beta 1 hat. And I'll look here at the first slope coefficient. I could have just as well put a 2 or 3 or 4 here, so the labeling doesn't matter. You can relabel the regressors however you like. So whatever we learn now about the behavior of beta 1 hat will then also be true for the behavior of beta 2, beta 3 hat, and so on. So what is our estimator beta 1 hat? Well, like any estimator, it consists of two things. First off, a rule for computing estimates. On a data set. So if you have a data set, so you have certain columns of numbers, then there's a rule that tells you how to combine these numbers into an estimate, so into a new number. And we're wondering now, is this rule that the Ols Estimator is using a good rule? What would it mean to be a good rule? Well, we have to remember what our ultimate goal is, and our ultimate goal is to estimate beta 1. And beta 1 is something that we cannot see. It's a population parameter, right? So it's a property of the population, and it tells us something about, so we have tied it to the true causal effects, so it's something that we really want to learn. So does our rule teach us about beta 1? Well, that really depends on the data that we're using, right? We cannot just make up whatever data we want, then apply the Ols Estimator and hope to learn about beta 1. That obviously doesn't work, so we have to tie our data in some way to the population. And that is what the second property of an estimator does, is that it specifies data collection. And in our case, so we have assumed that the data is generated by drawing a random sample from the population. So this establishes a link between the data and the population. And this link is important, for without this link, there's no hope that we can use our data to learn about beta 1. Since the estimator depends on a random sample, it is a function of a random sample, so it's also random. So we're taking basically the viewpoint from before we draw the sample, and we treat the estimator as a random quantity. So it's a random quantity, and it has some variance. So it's a random variable, and it has positive variance, right? So sometimes it will be a little larger, sometimes it will be a smaller number, and this is called sampling error. Depending on what kind of random sample we draw, beta 1 hat will be a slightly different number. So it's clearly too much to ask that beta 1 hat should always give us the true slope coefficient. That won't work, right? So beta 1 hat will sometimes be too large, sometimes be too small. But we can still say that beta 1 hat is a good estimator. And in this chapter, we're gonna specify some measures and look at some measures that look at sort of how good beta 1 hat is at estimating beta 1, even if it will never, if we can't expect it to always guess the correct value. In a sense, it's still a good estimator. it is not easy to evaluate the performance of our Ols Estimator Beta 1 hat, and that's mainly for two reasons. The first reason is that while we can apply our estimator to data and compute estimates, there's no way for us to know whether the estimates are good or bad because, we don't have the true Beta 1 to compare them to. We don't know what the true population coefficient is, right? Well, even if we knew the true population coefficient so that we could determine the quality of our estimates, still typically we would only have one random draw from our population. We would only have one data set. And so while suppose that for this one data set the estimator works well, there's no way for us to know that if we had drawn a slightly different sample, we would also have gotten a good result. So evaluating the quality of the Ols estimator using real data that you have maybe collected in the field typically doesn't work well. So what we do instead is that we evaluate the performance of the Ols estimator in a controlled setting using a simulation experiment so that we conduct using a computer. So such a computer simulation is called a Monte Carlo experiment. And in the Monte Carlo experiment, we can do two things. So we can control what the population model or what the DGP is, and we control it because basically we use a computer programming language to specify the model. So we have specified it, we know what it is, and we can simulate the process of drawing from this population as many times as we want. For the simulation experiment that I want to show you here, I have simulated the model, a very simple linear regression model, where y is given by, intercept is 0, then 1 times x1 plus 1 times x2. So both slope coefficients are 1, and obviously we also have an unobserved component. So how do we use this Monte Carlo experiment to learn about the distribution of Beta 1 hat? So we want to we draw multiple times from the distribution of Beta 1 hat. It is a random variable, so it has a distribution. And the way we draw from its distribution is that we draw a sample of size n, so I specify what n is, so it could be 50, 100, from our population model, from our DGP. So let's call the sample omega 1. And then we take omega 1 and we apply our OLS rule for computing estimate, and we can compute an estimate Beta 1 hat evaluated at sample omega 1. And then we repeat this process and we get a different sample, let's call it omega 2, right? And we can compute another estimate and then another estimate and so on. And we repeat this process s times, and then we obtain s estimates. And if s is very large, then we hope that the empirical distribution that we have just generated will be very similar or almost identical to the true sampling distribution or the true population distribution of Beta 1 hat. And the reason that we can hope that this is the case is a mathematical law that is called the law of large numbers. So I have conducted this simulation experiment for the population model that I specified, and I've set the sample size to be n equal 50. And then I have computed lots and lots of estimates for lots and lots of different samples, 1,000 to be precise. So all of these estimates were a little different, and they took values somewhere on here on this horizontal axis. And so what I've done here is I've drawn a histogram. So these steps are a histogram that give us the frequencies of certain value ranges for the estimates. So the bigger the bar of the histogram, so the more often, the more estimates had values in the specific value range. I've also drawn a density curve that approximates the histogram. So this density curve is our, given my simulation result, our best guess of the of the distribution of beta 1 hat for this population model and for this particular sample size and so on. As you might remember, when I wrote down the population model, is that the true coefficient of the regressor x1 was 1, right? So 1 is the true value that we want to estimate. So unsurprisingly, we're not always very close to 1, which is what we ideally want to have, but we knew from the start that that wasn't going to happen. So our distribution has positive variance, it is spread out. However, what we do have is that the distribution of beta 1 hat is centered at 1, right? So 1 is directly at the center of the distribution. So at least sort of the distribution of beta 1 hat is concentrating around the true value. And that is actually a general property of the Ols estimator that is called unbiasedness. So let's talk about unbiasedness. Unbiasedness. So in any linear regression model that satisfies certain assumptions, we will have unbiased estimates, and I'll be very precise about what that means in a second. So we need some assumptions for this to be true. In particular, we need our assumption Ols1, and it was the functional form assumption. We need our assumption Ols2, and that was our exogeneity assumption. We need our assumption Ols3, that was our full rank assumption. And we need our assumption Ols4, and that is the random sampling assumption. And so we can distinguish these first three assumptions from the last one, so they are slightly different. So the first three ones are assumptions about the population model. So assumptions about the DGP, right? So remember, we think of it like this, so that there's an actual population model out there, but it is, well, we cannot see it. It's still there. And we're assuming that this population model satisfies certain assumptions. And so we're assuming basically that we write down a linear regression model that captures the DGP exactly. Even though sort of our linear regression model has degrees of freedom, right? We're not pinning down, for example, the values of the coefficients, but we are pinning down a lot of the structure, and we are assuming that this is the correct structure. So we're making some assumption about something that we don't see. So these three assumptions are very hard to verify. We basically have to argue them, and we have to use our economic intuition to make an argument that they are good assumptions and that they are reasonable. The last assumption is assumption about data collection. So this is a little different because we know how we are collecting our data. So OLS4 is something that we should be able to verify. Now, if these four assumptions hold, then the expected value of beta 1 hat is equal to beta 1. So this is called beta 1 hat is unbiased for beta 1. And so how do we interpret this? We could say, well, on average, we are estimating the correct value. We can also interpret this, since the expectation of a random variable, we interpret it as the center of a distribution. We can say the center of the distribution of the estimator is the true value. And we can also interpret it as a prediction. So if we have to predict what we are going to estimate, well, we make that prediction before we draw a sample, then we would say our best prediction is that we will estimate the true value. Here again, I've plotted the simulated distribution of beta 1 hat, and it was simulated under certain assumptions about the DGP, about the sample size. So an interesting question to ask is, how does this distribution change if I change some of the parameters of my simulation? For example, one thing that I could change is the sample size. Here I've chosen sample size n equal 50. How would the distribution look like if I choose a larger sample size, such as 100, for example? So this is exactly what I'm going to look at next. So I'm not just simulating the distribution for n equal 50, but also for larger sample sizes, and we see how that changed the distribution. So here is a summary of the simulation results. The first panel here has sample size n equal 50, so it's just the same graph that you've seen before. It looks a little different because the scaling is different, but it's really exactly the same graph. And now as we move from the first panel to the second panel, so that corresponds to a doubling of the sample size, going from n equal 50 to going n equal 100, and that changes the distribution. As we can see, the distribution is still centered at 1 at the true value. Very nice, but also not unexpected, because we know that unbiasedness is a general property of the Ols estimator under certain assumptions. But what does change is that as we increase the sample size, the distribution becomes less spread out, and it concentrates more tightly around the true value. And as we even increase the sample size further, so we double it once again, so we go from 100 to 200, and the sample size, sampling distribution of the estimator becomes even less spread out and concentrates even more around the true value. And so we could continue like this, and we would see more of that happening. So the distribution concentrating more and more around the true value as we draw larger samples. And this is also a general property of the Ols estimator, and it's called consistency. So we want to look at consistency of the Ols estimator. Just like unbiasedness, consistency is a property that holds generally for the Ols estimator under some general assumptions. So if Ols 1 through Ols 4 hold, then what we can do is we can take samples of increasing size. So we take the sample size n to be bigger and bigger, and we keep increasing it, or we take, mathematically we write it as we take n to infinity. And as we continue this process, what happens is that the distribution of beta 1 hat concentrates more and more around the true value, beta 1. So as we increase the sample size, basically we diminish the risk of having realizations that are far from the truth. And we say beta hat 1 is consistent for beta 1. And so what we can do, so we can be a little imprecise, but basically what this means, if we choose our sample size very, very large, then this process here has progressed very far. So that means that we are very, very tightly concentrated around the true value. And that means we can, for all intents and purposes, we can assume that beta 1 hat is practically equal to beta 1 if the sample is very large. And we will use, heuristically, we will use such relationships later on. So this is very informal notation that we just use for this course, where we don't want to emphasize the mathematics. Clearly saying that the distribution of beta 1 hat concentrates more and more around the truth. Well, given that beta 1 hat is unbiased, this is equivalent to saying that the variance of beta 1 hat is becoming smaller and smaller as the sample size increases. So as the sample size increases, variance is decreasing. And so this is what we're going to do next. We're going to look at the variance in more detail, and we will see, we will be able to say more about the relationship between the variance and the sample size.